Swayam Prabha. Digital India. Educated India.
So in this lecture, we are going to cover the non-uniform axial loading. So as you can tell from the name itself, it comprises of structures or members where the load, the axial load, is not uniformed across that entire length of the member. It varies depending upon where you are looking at. Right. So before we begin into the concept of the non-uniform axial loading, and this is probably the topic where for the first time you are going to appreciate the concept of the internal stresses that we have been talking about, since the day one of our lecture series. Right. So first we are going to look at some cases of the uniform axial loading, which you have already seen in the previous lectures, before moving on to the non-uniform part. So as you know already that for the uniform axial loading, which we have looked at, for example, one example can be this one over here. You have sort of a cantilever bar, maybe weightless for this particular case. You are pulling it with a force P over here, which automatically means that you will have a reaction force going on the other side, maybe something like this, right? So you will have a reaction force equal and opposite P over here, right? Or if you're looking at this particular bar in 2 dimension, it may look something like this, where you have a reaction force P over here, another reaction force P over here, right? So now let's go ahead and look at what we have been talking about, these internal stresses which are there. Now, if I take this bar which you have over here, and suppose if I break it into 2 components, so if I take a section, a particular section, say somewhere around here, and say this is my left end and this is my right end over here. Now if I have to draw the free body diagram of the left end, remember the whole bar by itself is in equilibrium, so the individual parts must also be in equilibrium. So if I go ahead and draw the free body diagram of the left end, which is over here, so this is my left end L. In this one I know that I have this particular force P, right, on the left side. So to balance this one on this particular side, at where I have exactly cut this section over here, I must have an equal and opposite force P over here, right? Similarly, if I'm now looking at this right end over here, and if I draw the free body diagram of the right end, right, suppose this is my right end again, right? So here in this right end, I have, because of this particular force P which is acting to along this direction, I will have an equal and opposite force here, because remember this section is not going anywhere, the section itself is in equilibrium. So here I will have another force P equal and opposite to this P over here, and as you can tell, it's sort of a self-balancing system, because on the right I have another force P over here, right? So the whole system is in equilibrium, so the individual parts are also in equilibrium, right? So this is my right hand part, this is the right. Okay, now if I have to discretize it even further, for example in this section over here, if I may have to go and cut another smaller section over here, and if I take a look at this particular section which I just cut, what do I have? So if I take a look at this one, right, if I take a look at this one, and for that small section which I just cut over here, right, which is essentially this which is essentially this section over here, here I have a force P which is this particular force over here, this is this force P, right? Now to balance this one over here, so this balance to this particular force, I must have an equal and opposite force P over here, right? So as you can tell that every smaller chunk is in a state of equilibrium. Now instead of taking this one, if I take this particular section again, that will also have a force P and an equal and opposite force P to balance this particular P over here. So maybe I draw this particular section, if I draw this particular left half of this small chunk that I have, so if I have to draw that one again, I will have something like this, where to balance this P I will have a P over here, and the original P is already here, right? So essentially it's a self-balancing system. So you see every individual chunk you take within this bar which is under this uniform axial load, it has the same load P. So that means that tells that is where this word uniform comes into play over here, right? It is the same, every individual cross section has the same uniform load P which is over there, right? Which is probably more better understood over here in this particular figure. If I take this bar and if I chop it off into smaller tiny bits, so this may be my left end and this is probably my right end. I've taken this whole bar and blown it up. Every individual section is in this state of the small p. You can also maybe visualize over here. Once I have this one, if I'm stretching it, right, every section is sort of moving, or if I compress it, every section is getting sort of compressed. Right. So now if you see this one, now remember that formula that we had looked at, that was your delta was P times L divided by A times E. We had looked at this one over here, right? So if you look at this one, and if these individual members say are of maybe length dx, right? If these individual tiny bits are of length dx, right? For this individual chunk which is of particular length dx, if I have to write the deformation of that one, so that will be your d of delta will be equals to P times dx divided by A times E, assuming that in the prismatic bar the area cross section remains the same, right? So as you can tell, for these individual chunks I have this d delta. So now if you take all of these chunks which are there, all of them together, so you have d delta plus d delta plus d delta and so on and so forth, which eventually gives you this delta because your dx plus dx plus dx adds up to the total length L. In another way, you can imagine that you are essentially integrating across the entire length of the bar, right? So this is how you get the total deformation delta equals to PL divided by AE, right? So this is an example of the uniform axial load where the P is essentially same throughout this entire length of this particular bar that you have over here, right? Now let's move on to look at some of the examples of the non-uniform case, of the non-uniform load. Right. So if I take a look at the example of the non-uniform load, these are some of the very typical examples that you have. Right? For example, here the first figure, let me call this as maybe figure A. Right. What you have over here, you have along the axis, you have loads which are varying at different sections. So instead of just having a P at the very end, you have a PB over here, PC over here, and you have a fixed support over here, which is also transmitting some axial load to keep this entire bar in equilibrium when you have these different forces, right? You can have, but note one thing, in this figure A, the area of cross section is the same, right? You can have something which is like this one, this figure over here. So let me maybe call this B, case B, right? So in case B, you have the loads which are different, and also the area of cross section that is also changing depending upon where you are along the length of the bar, right? But it is discrete changes. Along this length L1, you have a particular area of cross section. Then when you are going to length L2, you have a different area of cross section over here, right? Now, as opposed to that, you can have another case where it is case C over here, where you can have the area of the cross section which is changing continuously, you have a continuous gradation, and you have a load P which is acting along that entire length. This is the per unit length load that you have, and this is a sort of a uniform load. You can have a non-uniform load as well. You can have many different cases, but overall these are the main three cases, so A, B and C, that we have over here, right? So now what we are going to do is that we are going to look at these you are going to look at this non-uniform axial loading, how the internal stresses change, right? So before we go into taking a look at this non-uniform axial loading, how the internal stresses change or vary throughout this particular length, let's again go back and visit that how for the uniform axial load it is going to change. So before that, we are going to start with the part A that we looked at over here. Remember that this was the part A, this one. So we are going to look at these cases individually. We are looking at A, B and C, and we will see how the formulations and everything vary. So the part A is this one where you have same area of cross section. So maybe I will just probably explicitly write it here, that your cross sectional area is constant, right? Something like this. And a practical example for this one is these braced columns. You have columns in the building or a structure. Now in addition to carrying a vertical load maybe from the top, you have these bracing systems at the left and the right, which may be also imposing, you know, additional loads in this part. In addition to these axial loads, you will have moments as well, but you get the idea, right? Our topic as of now, it focuses only on the axial load part. Moments we will deal with later. Right? Or the other case which I showed you, something like this over here, where you have, you know, non-uniform discrete loads along the length of the member that you have, right? So if we have to go ahead and understand that how the internal stresses vary, first let's take a look at the ones with a uniform axial load, right? So as you can see over here that we have a bar, and here I've just presented with numbers so that, you know, numerically it's easier to understand. We are engineers, so we love working with numbers. So for this one, if I have to draw the variation of the internal stress along the length of the bar, so maybe let me just draw this axis that is over here, that I'm going to draw, you know, this particular axis. So here my vertical axis is maybe the internal stress N, right? So this is my internal stress, right? And the horizontal axis, this particular axis is X, which is the length of the bar that I have over here, right? So as we had seen, remember that in this one bar, if I come and if I take a section over here, right, and if I draw the free body diagram of this particular section, what I essentially get is that I have a load of 8 over here. So correspondingly at the other place also where I am cutting this particular section, I must have 8 kilonewton at that particular section as well, right? So it doesn't really matter that where you are taking this section. Is this section, even if you take closer to this edge or farther away or farther away. So essentially if I take the section here or here or here or here, it really doesn't matter. Everywhere, if you draw the free body diagrams, you are going to get the same uniform stress of 8 kilonewton, right? So if on this axis which I drew, and remember this 8, I mean the internal stresses, this is the internal stress I'm looking at. So this is N, right? So wherever I'm chopping, I'm calculating what is that internal stress N, right? So everywhere if I am drawing this internal stress along the particular length, I'm going to get one constant line of 8 kilonewton. So if I have to represent that one over here on this same diagram again, what I will have a constant internal stress up to, as you can tell, from up to this particular point that is there, right? I'm going to have the same internal stress of 8 kilonewton. Okay, so this is 8 kilonewton. This is the internal stress of 8 kilonewton that I have over here, constant throughout that entire length, right? Now this is the case of the uniform axial load. Now let's go back and check that once we have these non-uniform loads, how does the internal stresses vary? And also just to mark it here, that one of our typical conventions is that tensile is positive. So if I take an individual section as I did here, the section is in tension. So when we have this 8 kilonewton on the left, you have the 8 kilonewton, a pulling kind of a mechanism. So that is typically represented as a positive quantity. That's why I do this diagram on the upper half, right? So this is a positive stress that you have over here. This is positive, right? So let's look at the non-uniform axial loading now. Now, as you can tell, now life is going to become slightly more complicated in this particular case, right? So what are we going to have? So let's look at it closely. So if I have this non-uniform axial load, now suppose, as you can tell, that I have 3 distinct sections over here. I have a 5 kilonewton over here. At the point B, I'm applying this 8 kilonewton. At the point C, 4 kilonewton, and at the very right, I have 7 kilonewton. So first, even before trying to go ahead and solve it, let's first check that whether this particular structure is in equilibrium or not. Is it? I have a 7 and a 5 which is going towards the left as a total of 12 kilonewton, and I have a 8 and a 4 which is going towards the right as a total of 12 kilonewton. So the 12 and the 12 balances. So yes, my structure is in equilibrium. So now that I have determined that my structure is in equilibrium, let me go ahead and draw the internal stresses that are there, or try to at least figure out what the internal stresses would be. Right, so let me mark these discrete sections with this discrete numbering. So for the first section A to B, as I said, there are 3 sections, 1, 2 and 3. So let me just go ahead and mark them. For the first section A to B, I'm going to mark it as the first section 1 over here, right? From B to C, I'm going to mark this is a section 2, and from C to D, I'm going to mark at section 3 over here. Right, okay. So now let me look at these sections individually. So let me first look at the section 1 that is over here. Now in section 1, while I am at this particular section, if I draw the free body diagram of any individual parts, I have again taken a small chunk of that one. So if I draw the free body diagram of this part over here, what I will essentially get is that I have a 5 kilonewton here. So to balance that, I must have a 5 kilonewton here. Right, now it doesn't matter at anywhere within AB if I was taking the section, if I'm taking the section over here, or if I am taking the section maybe at here, right? And if I draw the free body diagram, I'm going to have essentially the same 5 over here, right? So this internal force that I have, I'm going to, since I'm talking about section 1, I'm going to call, this one as maybe the internal force is N1, right? So all along this entire section of 1 over here, I have this internal force N1 as 5 kilonewton over here. And as you can tell, the nature is going to be tensile, so I'm going to mark it as a positive 5. So I have in this entire section 1, I'm going to have an N1 which is equals to 5 kilonewton, right? Okay. Now let's come back to section 2. So section 1, depending upon whether I'm taking here or at the very end, very near to B, maybe just to the left of B, if I take, I will have the same force of 5 kilonewton, right? Now at exactly the point B, I'm applying this another load of 8 kilonewton. So I'm going to have a jump in the loads. I'm going to have a discontinuity over there. Now, while I'm in section 2, let me again draw a free body diagram of a chunk over there, right? So while I'm at section 2, if I take another breakage point over there, and if I have to draw the free body diagram of this entire chunk that I have, so essentially from this particular end to this end over here, the free body diagram of that may be looking something like this over here, right? So here in this one, I have this externally applied load 5 kilonewton, right? Now at this particular point I have, so this is my point A. Now at intermediate point B over here, if this is my point B, at point B I have a load which is 8 kilonewton which is acting over here, right? So at this breakage point, which is essentially this breakage point over here, so just maybe let me mark it, right? At this particular breakage point that I have, right? So here to balance this 8 and a 5, where 8 is going to the right over here, 5 is going to the left over here, I must have an internal force which I am going to call as N2, since I am looking at section 2 over here. This internal force must be 8 minus 5, 3, acting in this particular direction to keep my entire section is in equilibrium. So this is 3 kilonewton, right? So again, it doesn't matter where I take this section between B to C, just to the right of B and just to the left of C. If I take this section anywhere here or anywhere here, everywhere, because of equilibrium, I am going to get this force which is pointing towards the inside of the cross section of 3 kilonewton, right? Now as you can tell, this cross section will be in compression because this force is trying to push the member inside, so it is going to be in compression over here, right? So if I have to go and for this section B to C, a more correct way to say that is just to the right of B and just to the left of C. So in this section B to C, what I will have that in section 2, I will have my N of 2 as minus 3 kilonewton, the internal force as minus 3 kilonewton, right? Okay. Now I am left with one last section, that is the section 3 over here, and now you have got a pretty good hang of the idea that you have. So if I'm in this section 3 over here, and if I am drawing maybe another section over here, and if you have now two ways to do it. You can maybe take that entire length from A to where you have cut, or the easier way to balance the forces and do the equilibrium equation is maybe just to take this particular section over here. Whether you start from the left or start from the right, you're eventually going to get the same thing because your section is in equilibrium. So if I take this particular section over here, and if I draw the free body diagram of this particular part, what I'm going to have is something like this, right? Where here I have this force of 7 kilonewton. To balance this one, and this is where I cut my section, to balance this one I must have an equal and opposite force of 7 kilonewton, right? Now instead of taking this one, if you had taken this entire section over here, this entire section, you would have gotten the same. You would have gotten, you see, you have 8 plus 4, 12 going to the right, and you have a 5 going to the left. So 12 minus 5 was 7, and that force would have been acting in this particular direction. In this direction, essentially telling it's a compressive. It will be equal and opposite to this 7 that you have over here, right? So this one, this 7 which I wrote, is going to be my internal force, maybe N3, which is equals to the 7 kilonewton that you have over here, right? So, and again you see this section is in compression, this is in compression over here, so this is going to be a minus 7. It is essentially compressive, right? So I am going to write here for this section N3 I get as minus 7 kilonewton, right? So is that clear? So in the first I have an expansive force. In the section 1 I have an expansive force of 5. In the section 2 I have a compressive force of minus 3, and in this particular one, sorry, my video overlaid, so I am going to write this once again, right? So what I essentially wanted to write was my N3 was minus 7 kilonewton, right? So for section 2 I have a minus 3, and here I have a minus 7 kilonewton. So again a compressive force of a minus 7, right? Okay, now you see that how the game changes when you were talking about the uniform axial load. So now you have discrete sections where these internal forces, the N1, the N2 and the N3, it varies where you are. So in the section 1 I have a constant internal force of 5 kilonewton, expansive or tensile. In the section 2 I have another uniform load of minus 3 across the entire from B to C. In section 3 I have another uniform load of minus 7 kilonewton compressive, right? So in between these individual chunks of A to B, B to C, C to D, I have these uniform loads, but if I take a look at that entire bar, that load is non-uniform. In the first part it is 5, in the next part it is minus 3, in the next part it is minus 7, right? So now that we have this kind of a case, right? So how is the total deformation going to be? Previously it was easy, it was just delta equals to PL divided by AE. Now how the total deformation is going to vary? Now let me present to you a cleaner figure of this one, now that we have understood how that internal stresses vary. Now remember, before we go to the next page, I have this positive 5 over here, negative 3 over here, and a negative 7 over here. So let's go to the next page and see the internal stress distribution. This is, again, remember, this is similar to what we saw before. This is the distribution of the internal stresses, right? So N is the internal stresses. So let me explicitly write that. So N is the internal stress, right? So as we saw, from A to B I am going to have a positive 5 kilonewton, from B to C a negative 3 kilonewton, from C to D a negative 7 kilonewton, as we saw in the previous slide as we calculated the internal forces by taking these cross sections over here. Now, can you tell me what is going to be the deformation of the total bar? Well, to look at the deformation of the total bar, let's again look at these individual bits. So for this particular section from A to B, the internal deformation, and again if I have to mark these sections as 1, 2 and 3, right? For the first one, I'm going to have delta 1 will be equal to 5 times length of AB divided by the area times E. A and E is the same across this entire length, right? For the second one, your delta 2 is going to be minus 3 times L of BC divided by AE, right? Indicating this negative, indicating you're going to have a compression in the BC. And lastly, for this one, my delta 3 is going to be minus of 7 times the length of the member CD divided by A times E, right? So we have these individual deformations. What is going to be my now total deformation of the entire bar from A to D? You are right. The total deformation delta, the overall delta, it is simply going to be equals to delta 1 plus delta 2 plus delta 3. Beautiful. Right, so this is the total deformation that I have, right? So I hope this is clear to you that how, due to non-uniform axial loads, this overall, this displacement sort of, we calculate it for the individual chunks and then we sort of add it all together. Now, another example just to reinforce the concept in your mind is that if you take a look at this one, it is essentially the exact similar case as you had before. You have this particular bar with this individual discrete loads PB over here, PC over here, PD over here, and this is fixed at A. Again, if you cut individual sections and if you look at the internal stresses, for example, for the first one, for the so again, if I have to mark this as section 1, this is section 2 and this is section 3, right? So here if I cut at a random point, if I cut a cross section, I am going to have this particular force N1, which is, if I just balance out these particular forces, I am going to have N1 equals to minus PB plus PC plus PD. As you can tell, PC and PD are acting in the vertically opposite direction that we have, and we have this PB which is acting vertically up over here, so that sort of takes care of this particular equation. Then for N2, if I draw another section over here, I am going to have N2 as PC plus PD, as you can tell from this one. And for the last one, if I take a random section, maybe somewhere over here, I am going to have N3, which is going to be equal to the PD that I have over here, right? So now again, similar to the previous case, now I have, for these individual chunks, I have these internal forces. So what I can do is that I can go ahead and calculate the different deltas, right? So for the first section, again, so let me mark it, section 1, 2 and 3. For the first section, I am going to have the delta 1 as N1 L1 by AE, delta 2 and the delta 3. So we get the individual deformations. Once we have the individual deformations, we can add all these deformations up. Yeah, so your total delta for this entire bar from A to D over here, it's going to be the sum of the individual deformation of the individual deltas that you have over here, right? So if I have to write this entire thing in a nutshell, what I essentially get is that my delta that I have, right, this delta, I can maybe write this as delta as a generic formula. I can write delta as summation of Ni Li divided by A times E. The internal forces times those individual lengths divided by the area of cross section, which is constant throughout this entire length, times the Young's modulus, which is constant if you're looking at a bar which is made of one single material, right? So this is an important relationship that we just learned today, that your total delta is equals to summation of Ni Li divided by Ei that you have over here. right? Okay, so I hope this one made sense to you. So we are going to look at, so until now we looked at this particular case A that is there. So we are going to look at further cases. Like, remember, our case B was, again, we have discrete loads, but at the same time we have different cross sections. Now, can you tell from what we just learned before, and if we analogically apply the similar concept, what is going to be the delta for this one? Yes, you have guessed it very right. Remember, in the previous one, if I have to just go back to the previous page, it was Ni Li by Ae. The only thing that is changing is this A over here. So this A, for the case of the discrete cross section, it is changing, right? So the only difference to this formula is going to be, if I have to write the delta, it is going to be Ni Li divided by Ei times C. I am still assuming the material is the same throughout. So the only thing that is changing is the area of cross section, depending upon which section you are looking at. So here I may have cross section 1 and I have the 2 over here, where your A1 for the cross section 1 is different than the A2 for the cross section 2, right? So you may have different things. Now, here, as you can see in this example, if we have different materials also, like if we have E1 for here and E2 over here, what is going to change in this equation? It is simply going to be Ni Li by Ai Ei. So this is the overall, the most generic formula that you can get. So let me maybe border and broader properly, as unlike I did in the previous page, something like this over here. So the overall delta, sorry, I forgot to put the summation sign. It is going to be the summation of this entire thing, Ni Li divided by Ai Ei, as I had for the previous page. So this for the total summation over here, and this one is a more generic formula that you get. So sum of these individual deformations is going to give you the total deformation, right? Okay, so that helps us solve case A and case B. So let's go to the last case now, which is my case C over here. This is interesting. So in case C, that you have the member where the area is uniformly grading, uniformly decreasing from the left end A to the right end B over here. Now here the question is that how, for this member, how am I going to calculate the delta? Now remember that he also has this px which is going throughout, and as usual our assumption here is that this bar is weightless, so you only have this axial load which is acting, right? So as you can tell, and for this you guys are very good at it, as you can understand that we are going to apply some of the principles of integration in this one. So if I have to take a small chunk of dx, of length dx over here, right? So if I have to go over here, right, if I separate a small chunk, and this is my dx over here and this is the left half. So again, if I have to write it over here, so this is my left half and this is my right half over here, where I have taken this individual section dx. So if I am looking at this equilibrium of this particular element dx, right, assuming that this length is extremely small over here, so I am going to have my d of delta, it is going to be n of x dx. Remember, pl divided by ae, my p is the n of x, l is the d of x for this individual chunk I'm looking at, divided by my area of cross section is also varying across this entire length. So I have the a of x, right? Say for this small discrete, the area is a of x over here, and let's assume that the Young's modulus is same across for this particular material times E, right? So this kind of gives you that for this one, if I have to calculate the overall delta, it is going to be simply the integral from 0, that is from the left end to the right end over here, 0 to L, same expression, n of x d of x divided by a of x times E, right? So this is the generic formula that you get for this one over here, right? Now you might be wondering what is n of x, because this keeps changing throughout, right? So the generic formula for that one, if you take a look at this figure over here, remember this is my left half of the wherever I drew this particular cross section. Now if I look at the right half, how is the right half going to look like? Let me try to draw it for you. So the right half is going to be, you know, this tapering section that is there, right? So this is my right half R over here. So here also I am going to have, just to balance it out, I am going to have this load of n of x, right? Now remember that here I have this small p which is acting throughout. So let me mark that also. So I have, you know, this small p of x which is acting throughout. So as you can tell from equilibrium, my n of x would be integral from, if I'm talking about the equilibrium of this right half over here, across this entire length. So this length, this particular length is going to be what? This particular length is your L minus x, because this section I've taken as x over here, right? So this is going to be L minus x, right? So if I have to write it in terms of the formulation that I have over here, so this is going to be, this integral is going to go from x to this particular length L, which is over here. So this integral is going to go from x to L, right? P of x dx, right? So this is that n of x which you are going to substitute in this one over here, right? So I hope you understood how we got the n of x, which is essentially we are doing the equilibrium of this one. So this goes from this particular point x to this entire length. So this is the total force which is being balanced by this this internal force nx, and this internal force by definition, since we are cutting a section, is equal to this nx that we have over here, right? So now that we have understood the three different cases, the first one with the uniform cross section, second one the non-uniform cross section but discrete, and this last one C over here with a continuous gradation of cross section. So now we have understood that how we are going to calculate the deformation under these non-uniform axial loads. Next we are going to look at a very simple example just to understand that how to calculate these individual deformations which are there.